Thank you, Olivia. Thank you for the kind invitation and for this wonderful organization that you have done for the homage to the great Alexander Grothendieck. In my lecture, I will try to highlight some basic mathematical ideas of Grothendieck and how those basic mathematical ideas are related to more general understanding of culture and knowledge in general. So my presentation will be as follows. It will be also dedicated to the memory of Pierre Cartier, who died 3 months ago and who was a very kind collaborator of Grothendieck in the first stages of his life. And there is a beautiful article by Kohn and Cunir on the memory of Cartier, which they put in the archive just 3 days ago, exactly on the anniversary of Grothendieck's death. So you can go to that beautiful article in which they make a beautiful homage to Cartier. We dedicate this to Cartier and, of course, to Grothendieck. This is the content of my presentation. Essentially, I think that the work of Grothendieck can be divided in 4 essential decades. A first decade between his PhD thesis and the beginning of his work in the Institut d'études scientifiques. Then the second decade, the work that he did at the IHS. The third decade, the work that he did around Montpellier at the university and then around near Montpellier. And then the fourth decade, which is extremely little known and which has to be studied in the following decades, is the fourth decade between 1991 and 2000, in which he wrote a gigantic mass of work that we have still to understand what is happening there. I imagine that the public is extremely wide. Olivia is telling me that we have some hundreds of people listening. So I will try to go to very simple ideas, following the spirit of Grothendieck. Grothendieck always insisted that the deep ideas should be simple. Not necessarily the converse. Simple ideas shouldn't be deep normally. For example, stupid implications like P imply P is very simple. It doesn't have any depth on it. But in general, very deep ideas should be simple. He insisted on that. And I will try to show how some of those deep ideas are in fact extremely simple. Since we have an extremely wide and gigantic mass of work with Grothendieck, I will concentrate mainly on some 15 years between 1955 and 1970. That is the end of his first decade and his second decade, and will insist in some very simple ideas there. And I will pass quickly over some beautiful and great ideas also of the third decade. My main goal in this short lecture, I hope it will take a little more than 1 hour, is to show Grothendieck's search to understand multiplicity and unity through deep and soft perspectives. So the terms there are important: multiplicity and unity, and to understand them, how he cares about them using deep perspectives, which are related to a soft understanding of mathematics. This is a general look of Grothendieck's way of working, not just in mathematics, but also in knowledge and life, as Olivia was saying at the beginning of the presentation. Grothendieck was a very kind spirit, always open to a very wide pendulum between what we may call the many and the one, or the discrete and the continuous, or the algebraic and the topologic, or the particular and the universal, and more generally between the analytic and the synthetic. He was able to work on all those different views of the pendulum with an extreme depth, with a high technical achievements, but also with a wide vision. That's something very special in mathematician. It doesn't happen often. That's why we can call Grothendieck a genius. He was able to work on the very deep technicalities, but on the same time, those understood through a unitary vision of the mathematics and of the world. So that will be my main goal, to show this back and forth between multiplicity and unity related to deepness and softness. We know the life of Grothendieck, and thanks to the interviews that Olivia will be doing with the people that knew, especially close Grothendieck, we will see how he was an extremely kind spirit, a spirit with a very great humility, very humble spirit, and at the same time with that generosity that he had. Humility and generosity are some kinds of properties of Grothendieck's character, which are especially understood through all his life. He came home from very humble beginnings at what we may call a margin, the margin of Montpellier, which didn't have a strong mathematical tradition, but what you know very well, all the details, I will not go over them, how he was an incredible capacity to do mathematics on his own. But then afterwards, he entered the Séminaire Cartan at Paris, and then he under Dieudonné and Schwartz, he produced this gigantic PhD work on functional spaces. We will talk about that a little, if we may, in the question and answers, but I will not explicitly talk about the analysis, the functional analysis work now, because we had to restrict some part of the work. But there is an extremely beautiful article by Cartier and other articles also about the importance of Grothendieck's work on the nuclear spaces. It's on the Lecture Grothendieckien that Frédéric Jacques has edited some years ago. In that moment, between 1949 and 1970, little by little, he becomes one of the most respected and clearly one of the most prolific mathematicians of his times. And in the Great Center at the EHS, he produces a lot of mathematics. I will speak about some of those mathematics that are produced around the Great Center. But then afterwards, he has a fantastic work also done in Montpellier and in his third decade between 1981 and 1991, which beautiful mathematics, but also extremely profound physical, metaphysical, and philosophical thoughts about the words. Some of those great works were unpublished for a lot of time. Recoltes and Mike has been published like 2 or 3 years ago, and La Clé des Sons has been published this year with postface by Lafau. So these great gigantic understandings of the world in general are also now beginning to be better understood than before. Here we have some of the pictures of Grothendieck. You can see also always Grothendieck like smiling, like a very kind person, very benevolent, very dedicated to the others in his seminars or with his students. A very open person to mathematics, of course, inventing mathematics all the time, but very open to life also, to all the different possibilities that life offers. the interviews by Olivia Caramello with his students will show this in a moment. The multiplicity of the work of Grothendieck is truly gigantic, as you know. He published at least 10,000 pages of mathematics, which is something completely incredible. It doesn't happen often. It happens only sometime with some genius. Certainly, Grothendieck can be put on the rank of a genius like Riemann or Poincaré, or something very special that he was able to do with his own powerful ideas, but also with a fantastic school around him with great students, which helped him a lot, and with the gigantic generosity of Jean Dieudonné, which was his senior, but dedicated a good part of his life to work with the ideas of Grothendieck. And then there is this a gigantic mass of manuscripts that have to be sorted out in the future. There is the great manuscripts that Malgoire captured for us at Montpellier, some 10,000 pages, but then there is this gigantic mass of manuscripts that now are at the Bibliothèque Nationale de France, which must have a lot of fantastic work, both mathematical and philosophical and theological and mystical and historical. Grothendieck was a really gigantic mind in all of kinds of thought. And if he was a mathematical genius in the first 50, 60 years of his life, I do not see why he couldn't be like that at the end of his life also. That's something that has to be studied carefully. Many people have said, I think, in a wrong way, that Grothendieck went mad. I don't think at all that he was mad. And at the end of his life, he was also doing a lot of very, very important work that we have to understand in the future. So this gigantic multiplicity of work is also extremely can be understood through a Unitarian way in a lot of ways. I have here a small diagram. It's in Spanish because it comes from my Grothendieck seminar in Bogota. I couldn't have the time to translate it to English, but it more or less shows that in the first 30 years of his life, between 1950 and 1991, he more or less worked with a gigantic multiplicity of themes, like functional analysis, shifts, Hilbert spaces, Banach spaces, nuclear spaces, approximation, classic Riemann-Roch, holomorphic functions, Riemann sphere, tensor products, etc., cohomology. A lot of properties at the beginning of his life, very concrete work in his first years. Then afterwards, he extended that to a very wide understanding of mathematics through category theory, and particularly through schemes and topos. And then he comes back at the end of his life to very concrete studies around the Galois theory and the geometry that he invents in the 1983-84 non-abelian geometries, and then some kind of understanding of homotopy and homology at the same time with a unitary vision, which are the derivators. So in this quick diagram, you can see what I want to show in this quick diagram is you can see that you have a lot of multiplicity of ideas, but all of them are then extremely related together at a lot of moments of his life. He's able to work with multiplicity, but at the same time with a Unitarian vision of that multiplicity. So this comes to what will be my first lemma of my talk, is that one of Grothendieck's idea is that you understand unity through multiplicity. You multiply the world, you multiply the mathematics in very wide and different perspectives: topological, functional, complex variable, algebraic, categorical, and then with that multiplicity, you begin to thread together a lot of connections. With those connections, do you begin to understand in a unitarian way the world of mathematics. That's very, very Grothendieckien. You multiply, and you will see how this is extremely powerful technically. You multiply, and then with this multiplicity, you come to see a unity that was not visible at the beginning. Multiply and then unify. The influence of Grothendieck is extremely wide. One of the greatest influences in modern times, possibly the greatest mathematician of the last 50 years. And this goes to what is called the Grothendieck program. Many connections between algebra and geometry, between algebra and topology, and on the other hand, many connections between analysis and arithmetic, the Langlands program. Mathematicians who are able to go back and forth between the Langlands program and the Grothendieck program are mathematicians of the first rank. For example, Laforgue has been able to go back and forth between those two programs. That makes a great mathematician on himself. The influence of Grothendieck in the field's panorama is gigantic. Many of the most known, better known mathematicians of the last 50 years can be seen as direct or indirect heirs of Grothendieck. You can see here a lot of very brilliant mathematicians which follow part of Grothendieck's program. Well, let's go to some of the concrete possibilities that we can offer looking at Grothendieck. The first great gigantic work of Grothendieck is, as I was saying, his work on functional analysis and nuclear spaces and topological vector spaces. Between 1949 and 1953, he did his PhD, and then his great paper in Sao Paulo about the characterization of Hilbert spaces inside the Banach spaces. Those are great works, or in his what we could call his gigantic capacity of analytical calculations. Great calculations, long calculations with a very kind spirit in analysis. But then afterwards she shifts a little, and he goes to understand, to try to understand the synthetic aspects of algebraic geometry. There, the object, the technical object that changes completely his understanding of mathematics are the sheaves. Sheaves were then invented around 1943 by Leray in a concentration camp, and then advanced by Cartan and Serre in the school of Serre at the École Normale Supérieure. At that moment, Grothendieck appears at the École Normale, and he takes very quickly all the basic ideas of sheaves and produces wonderful works with sheaves from that moment on. Sheaves are the most simple technical mathematical object invented to capture the back and forth between the local and the global. You have just two topological spaces, one projected onto the other, and that projection is something which behaves well with the local properties of the space at the bottom, and the space in the upper hand is just like movement of the small sections of the space on the bottom, and injected in the global space. Go back and forth between a local and global, between multiplicity and unity, and then you have shifts. Shifts were coming from analytic continuation by Riemann in the 19th century, and then simplified by the school of Cartan and Serre at the École Normale, and produced a very simple object, mathematical objects, which will appear everywhere. Shifts come from complex variable, but then they go to differential geometry, to topology, to algebra, to logic. They are really everywhere. The first gigantic article by Grothendieck on this perspective is his well-known Tōku sur quelques points d'algèbre homologique. In the spirit of Grothendieck, always very long works, gigantic works. This is a 100 pages article, something that doesn't happen often. He was constantly producing very wide and very long articles with something extremely important for him, that the articles were very clear, extremely clear in their production. To understand Grothendieck, in fact, what one needs is time. To have enough time to read him with care, take 1 month to read with care with the Tōku, but after 1 month of reading the Tōku with care, then you will understand most of everything. That's something very particular and very special in Grothendieck. He was always extremely clear in his constructions. That clearness becoming like a kind of obsession in one moment of his life. The Tōku produces this beautiful connection, which will be also one of the constants of Grothendieck's understanding, a connection between Riemann and Galois. One can understand Grothendieck in many ways. One way of understanding Grothendieck is the one who understood really at depth what were the connections between Riemann's heritage and Galois' heritage. What he works a formal analogy between cohomology with coefficients on a shift, that is Riemann, and the series of derived functors or functors of modules, that is the Galois heritage. He shows that they come from a common root. And he then obtains natural bridges between a derived geometry, topology, complex variable, cohomology, using shift theory. Shift theory becomes the fundamental object there. And the categories of abelian shifts in particular are the kind of ultra paradigmatic example of what he will call abelian categories. He will axiomatize what is happening behind the categories of abelian shifts, good properties of factorizations in abelian categories. He introduces some axioms for those abelian categories, and he shows a very important result for the theory, that in a abelian category with a good axiom for infinities and the generator, then you can produce enough injectives in the categories, and with those enough injectives in the categories, you prove the formal analogy between the cohomology and the derived functors. Something beautiful appears here. In these infinitary methods, Grothendieck uses recursion theory, the transfinite recursion theory of Cantor, in all its length. Grothendieck will be known as one of the masters of category theory, but in this article, we can see that he was a master on set theory also, and the proof of this existence of enough injectives using transfinite recursion theory is an example of his great capabilities of analysis. So here, at the same time, we have a gigantic calculator and at the same time a gigantic envisioner, a gigantic synthetic envisioner of what is mathematics. He is able at the same time to understand synthetically what are the important best connections, but to show that they are constructed on a profound analysis. A profound analysis gives him the possibility to understand what are the synthetic forces behind that. That is something that also happens very rarely in mathematics. A great mathematician, perhaps one can say that a great mathematician should be at the same time be able to have a great capacity of analysis and a great capacity of synthesis. That doesn't happen often. Usually the normal mathematicians like us have a very small part, an understanding of a glimpse of analysis or a glimpse of synthesis, but to understand really in a complete way the synthesis and the analysis is reserved to very, very little mathematicians. Grothendieck was one of them. Here we have in this article also something which will be a systematic work of Grothendieck, a systematic back and forth between the many and the one. One of the beautiful and great ideas is that you will not be defining objects by its internal structure, analytical structure, but by external structure. So you are producing like a synthetic analysis, a synthetic understanding of analytical objects. You do not understand an object in itself, but we would say the object in otherness. The mass, the really fantastic mass of technical inventions of the Tohoku is wonderful. It goes from nothing, from really nothing, and it goes very, very far. This is one of the articles that I would recommend to people to read Grothendieck, because he goes very far, but little by little he introduces all the basic important constructions of category theory. In fact, MacLean, which was the inventor of category theory, always highlighted that the Tohoku was the fundamental article in which category theory came to life, because it produced amazing applications in the heart of mathematics. Indeed, the heart of mathematics would be this connection of Riemann and Galois. Another beautiful text of those years, we are in the years 1955, 1957. This is a fantastic work also of Grothendieck, of his ability of seeing things that the usual mathematicians were not able to see. The Riemann-Roch, the generalization of Riemann-Roch. The classical Riemann-Roch is one of the most beautiful works of algebraic geometry of the 19th century, in which Riemann had this fantastic and extremely deep idea that to understand the usual topological geometric invariant of a surface, which is the genus, the genus of the number of if you have a surface and you live on the surface and you look at the cuts on the surface, the number of cuts on the surface will give you an invariant of the surface. The genus and the sphere, if you have one cut in the sphere, then you separate it into parts, and so the genus will be by definition the number of cuts minus one. The genus will be zero. If you have a torus, if you cut once, it is still connected. You have to cut twice. You keep one. 2 minus 1 gives you 1. That's the genus of the torus, etc. That's a construction, an internal construction of a geometric invariant of the surface. And Riemann had this incredible idea that you could construct also that geometric invariant as an algebraic differential invariant going outside of the surface. You take the surface, and then you take all the good functions on the surface, the holomorphic functions, and then the bad functions on the surface, the meromorphic functions. Those gives you vector spaces. You take the dimensions of those vector spaces, the dimension of the meromorphics minus the dimension of the holomorphics gives you essentially the genus of the surface. So Riemann viewed or invented or discovered, that's an important question that also Grothendieck has good ways to answer. Do we invent or do we discover mathematics? He had very good ideas on that. Riemann discovered and invented this wonderful back and forth between topology and algebra and differential geometry. And he showed that those two invariants were essentially the same. It was a mystery. How that happened was completely a mystery, and I think that no one really understood the Riemann-Roch theorem before Grothendieck. Grothendieck, 100 years later, showed that this very profound and very surprising, amazing theorem was something which could be proved very naturally using a more abstract construction. Those abstract constructions are what is called the K theory by Grothendieck. Grothendieck takes over the surface. He takes good sheaves over the surface. Those are called the coherent sheaves that his friend Jean-Pierre had invented a little time before. He takes all the multiplicity of all coherent sheaves on the surface. That gives him a very interesting abstract group. And with these very interesting abstract groups, he connects this abstract group with the homology, and the good comparison between the abstract group and the cohomology gives him, in a very particular case, the Riemann-Roch formula. So he shows by a gigantic abstract construction, he shows how something very particularly happens. This comes to what could be my second lemma of my talk. The first lemma was we understand unity through multiplicity. The second lemma could be abstractions have a way to dissolve abstractions. We have abstractions, things in the particular that we don't really know why it is happening. But if we go to a wider margin, a more abstract margin, in those abstract margins, the abstractions disappear. And the disappearance of those abstractions explain what was happening in the particular. So abstraction is not invented per se, just to generalize. No, abstraction is produced because in the abstract realm, you have good connections. We have softness. We have deepness in the abstract realm. Then is projected into the particulars. So this is a constant manifestation of Grothendieck spirit is also. Abstractions dissolve obstructions. Abstractions dissolve obstructions. And that explains also why in the famous testimony by Deligne in one of Grothendieck's seminars at the EHS, Deligne said, after a lot of blackboards, gigantic blackboards, something very difficult in some sense at the end seemed completely simple, easy, soft. It was for Deligne a marvel, something marvelous. He couldn't understand why this happened. Conceptually, this happens because in the abstraction you dissolve obstructions. From the philosophical point of view, this means there are a lot of things that are connected to this. One of them is that in the back and forth between the one and the many, between, at the left, the universal, and right, the particular, at left, the integral, at right, the differential, at left, the understanding of something universal against something more related to the concrete. In this back and forth between the one and the many, one of the many important forces that Grothendieck's spirit produces to the philosophy of mathematics is that it produces a great inversion. Usually, we are in this realm, in the realm of types, the understanding of examples, of structures, existential structures. If you go beyond that and you go to category theory, then you look at not just existential, but unique existential, exists and unique. This is the way that category theory works, with axiomatizations of this kind of quantifier. Here we have the existential quantifier, and here we have a more precise existential unique quantifier. This gives you at right archetypes, which are projected onto the types. In this back and forth between the universal at right and the particularly at left, Grothendieck was a master in constructing archetypes. And with that, something very interesting appears, is that the archetypes are the dynamics of mathematics, and the types become the statics. Types are more restricted into particular spaces than the archetypes instead are flowing in a very soft way in this abstract world of Grothendieck. This abstraction, again, is not something artificial at all. It's completely natural, and this naturality is the one which gives deepness and softness to the constructions. They are not artificial in any sense. On the contrary, they are natural, smooth, thanks to multiplication. In the example of the Riemann-Roch, in Grothendieck's view, he takes all the coherent shifts. He multiplies, he takes all the coherent shifts at the same time. He naturalizes the construction. It gives him a smooth construction, and from that smooth construction, he proves that the types, from the perspective of the geometry, are the same thing as the types from the perspective of the algebraic differential perspective. So Riemann-Roch was types in the sense of geometric invariance for the genus, and then types for the algebraic differential invariance for the difference between meromorphic and holomorphics. Those are different types. The construction of Grothendieck shows that there is a wider archetype from which these archetypes are the particular perspective. Another way to show this back and forth, this constant back and forth between multiplicity and unity in Grothendieck through deepness and softness is one of the most important constructions of Grothendieck, the one who leads to his theory of topos. This is more or less well understood, and the school of Olivia Caramello at the Instituto Grothendieck is working for years to understand with very precise tools this heritage of Grothendieck toposes. But again, this comes from a unification of Riemann and Galois again. And for Riemann, a way to understand the curve was the dimension of the curve through the ring of meromorphic functions. For Galois, to understand the variety, the idea of number, was to understand the variety through the maximal ideas of the spectrum. And Grothendieck generalizes those two constructions at the same time. He takes a general unitary commutative ring. He takes the spectrum of A, generalizing it to prime ideas, takes the Sodaristy topology, and produces shifts over the spectrum of A that gives you a unification of Galois and Riemann, which will be the basis of the construction of shifts, of schemes. So, again, with Grothendieck, this is one of the lemmas, mottos, constant lemmas of Grothendieck. A space should not be rigid, sets should not be static. We should change things. We should move sets, produce variable sets that gives you preshifts. And if you put a topology on preshifts, then you get shifts. Categories of arbitrary shifts gives you the Grothendieck toposes. We will come back to this again in a moment, but this is certainly one of the 2 or 3 greatest inventions or discoveries of Grothendieck for his times and for the future times. We know that Grothendieck invented topos theory to solve very particular conjectures. We will come back to this in a moment. But they have, the toposes of Grothendieck have had also a strong influence in the development of mathematics afterwards. I will signal this in a moment. The idea is then that static points should not determine the geometry. There is something more soft which should determine the geometry. And in fact, topos do not have to be classical in general. A beautiful construction is that when you take the top of actions of a monoid on a set, that topos will be Boolean only if and only if M is a group. In general, we have to work with more soft structures and groups. Those soft structures and groups are monoids. And this shows a deep logic hidden behind, something that usually we cannot see with our simple eyes. 1958, finishing this fantastic, incredible first decade of Grothendieck, his Edinburgh lecture in the International Congress of Mathematics. This, contrary to the usual Grothendieck goes at length on strong, very detailed proofs to cover all the possibilities, to be extremely clear in what happens. This in fact, is a very different article in which he has a vision. He envisions something extremely powerful, extremely deep. This is very, very deep, what he sees in 1958, a very deep idea to solve the Weil conjectures. The Weil conjectures were stated like 10 years before by Andre Weil, and the very Weil had the idea that to show his conjectures, he had to introduce some kind of homology to capture those conjectures in number theory. In this presentation, which was a presentation at the International Congress of Mathematics, the cohomology theory of abstract algebraic varieties, Grothendieck has the vision of how to solve the Weil conjectures. The vision introduces the idea of schemes, which will be essentially sheaves with the basis with so over the spectrum of prime ideals, and with those schemes, he sees that there will be a good back and forth between algebraic varieties and cohomology groups of the field associated. There is here a back and forth between the understanding of number theory and algebraic theory and homology theory, and homology theory related, in fact, to some kinds of constructions with ramified spaces. Here is the impressive, very short statement that Grothendieck produces in that conference. Grothendieck says, to construct the Veil cohomology has to be defined by a completely different approach. He says, such an approach was recently suggested to me by the connections between shift-theoretic cohomology and cohomology of Galois groups on the one hand, and the classification of unramified coverings of variety on the other. So again, and permanently, he is here connecting Galois and Riemann. Galois with the groups and the cohomologies, and Riemann with the coverings. He has this wonderful idea that if he will be able to talk about these two great comings of 19th century mathematics in one universal construction, that will give him the way to prove the Veil conjectures. And he was able, in fact, to do that with a lot of work. This is the vision. The vision is stated in 3 lines, as you see, but then you have a lot of work, gigantic analytic work, architectonic work in all the following decade to show that this is in fact, that this will be in fact able to be true. So to prove that, he enters with Dieudonné. In fact, it's Dieudonné who is invited to the Institut Scientifique. And Dieudonné, with his characteristic generosity, says he will go to the IHS if and only if Grothendieck is invited also to the institute. And then Grothendieck enters the institute, and he works with Dieudonné and his students. His brilliant, extremely brilliant students. He had the chance to have brilliant students, but probably it's not a chance. The students were very brilliant because also they were his students. And between 1960 and 1970, he produces the gigantic Element de Géométrie algébrique with Dieudonné, and the gigantic SGA, the Séminaire de Géométrie algébrique, between 60 and 69 with his students. So this is a decade of work, constant work, with all his infinite analytical power to provide the foundations for his broad synthetic vision of what was important in category theory and what was important, the connection between Galois and Riemann and others. Here appear then the Grothendieck topologies, which are extremely simple, as always with Grothendieck. With the ideas are always, I insist on that, always extremely simple. Then the details have to be carefully written and understood through these gigantic thousands of pages, but the fundamental ideas are always very simple, because Grothendieck was always very consistent. If we are going to the depths, we have to be simple. So the idea of a Grothendieck topology is extremely simple. You simply change the idea of topology by coverings of open sets, by coverings by morphisms, and then the axioms of coverings by open sets could translate directly to axioms by coverings by morphisms. That gives you a Grothendieck topology in a general category. Then you have a wider margin. You go well beyond the category of sets. You go to any category in which you can work with a Grothendieck topology, and a site will then be an abstract notion of sheaf, in which you take all the possible sheaves on this Grothendieck topology. You take all of them together. That gives you a site. Sites are really fundamental to construct a a Grothendieck topology. What you do is essentially the generalization of a topological space. In a topological space, you take just the topology and the open covers, and then you take the sheaves over the open covers. That's a way of understanding the topological space analytically. But then you change things. Instead of working with analytical topology, you work with a synthetic topology, that is a Grothendieck topology. Then you take all sheaves on that Grothendieck topology. That gives you a topos, a category of all sheaves over the site. The site is just the category with the Grothendieck topology. On the bottom of the site, all the sheaves over the site. That gives you a universal construction. What is impressive is that in this universal construction, you get a deep structure that was not completely written on the site. There is extremely interesting back and forth between sites and toposes. That's something that the School of Olivia Caramello has been working extremely on the last 10, 15 years, the importance of the sites to understand the toposes. I will come back to that in a moment. But for the moment, then the toposes, the Grothendieck toposes, are a very simple idea. Generalize a topos, take all the sheaves on the topos, multiplicity, and the unity that you obtain of all the multiplicity of all the sheaves, then you get a deep structure. That deep structure comes from understanding the multiplicity through unity, you going through the synthetic perspective. These toposes were extremely important in many ways. I will mention. Well, I can mention them some now, for example. With these Grothendieck toposes, the School of Grothendieck, he himself and the School of Grothendieck afterwards were able to prove first in the 1970s with the Ligne, the Veil conjectures. The Veil conjectures are proved following the ideas of Grothendieck. The Ligne they diverted a little from the ideas of Grothendieck. He was not very happy about that, but essentially the nucleus of the basic ideas are in the Grothendieck toposes, in the construction of the étale topos of a scheme. With that, the School of Grothendieck was able to prove in the 70s the Veil conjectures, which was one of the most important open problems of the 1950s, of the mid-century. Well, after that, that's like a very big structural construction in order to soften the obstructions. Again, you construct this abstract because with that you will eliminate the obstructions and you will dissolve the problem, and then you will get the solution. It takes a lot of work to do all the details, but the general idea is again that one. You abstract in order to eliminate the obstructions. That's a structural approach, a very strong structural approach to what's happening with the conjectures. One of probably, again, at this moment today, the most important open problem in mathematics is still the Riemann hypothesis. The Riemann hypothesis, the great idea of introducing some kind of analytic functions by Riemann in order to connect them with the distribution of primes and the connections on deep connections of analytic complex variable with the algebraic theory of numbers. Those deep connections are stated in the Riemann hypothesis, still open today, but I think that the most interesting approach to solve the Riemann hypothesis has been the one that has produced Alan Kohn in the last 15 years, in which he has introduced a new topos, an arithmetic topos, in which he captures the Riemann hypothesis. With that, he produces a strong structural understanding of the Riemann hypothesis, something that the analytical perspectives didn't have. The analytical perspective had a lot of very precise calculations, but didn't have this big idea of capturing those analytical constructions by general structure. Has produced these topos. He hasn't been able to prove completely the Riemann hypothesis, but he has produced a path, a very strong structural path to show the hypothesis. In some time, probably it will work. That's another very impressive use of topos theories for very big open problems, Veil conjectures, Riemann hypothesis, and the work that is doing Olivia Caramello is also extremely interesting in this way, because Olivia, she has been doing is to use Grothendieck toposes to understand deeply the model theory of mathematics from a category theory perspective. Topos theory, I can go for the here perhaps. No, okay. No, let's just stay there. Then the topos theory in the 60s had then a construction afterwards, a simplification afterwards, which is called elementary toposes by Lovir and his school, which is extremely beautiful, extremely nice, but it simplifies the first construction by Grothendieck. The first construction by Grothendieck was much more deeper. It involved a lot of different perspectives, which cannot be reduced to just propositional or elementary ways of proofs. With topos theory, Lovir and his school showed that the natural, for example, that the natural intrinsic logical of elementary toposes is intuitionistic logic, for example, one of those beautiful propositional results that are obtained using elementary and propositional tools. But from there, the model theory mostly disappears. The richness of the model theory of the Grothendieck toposes disappears in this elementary topos perspective, which is extremely beautiful. I love a lot of that perspective, but I think it's a reduced perspective. The wider perspective, the more Grothendieckien in a spirit perspective, is to look at the model theory of the Grothendieck topologies and the sites. That is what Olivia has been doing systematically on the last 15 years. Going to the philosophy again and the methodologies, the problem between the one and the many, the fundamental problem, or between at left the continuous and right the discrete, at left universally, at right the particular, this back and forth corresponds now in these perspectives to the universal extensions of numbers produced by the schemes, in which the usual separations do not work anymore. In this general world of the schemes, you need some constructions which are not the usual separated real constructions, in which, for example, at right appear very naturally a lot of infinitesimals. At left, they disappear. So you have at right some kind of ideal archetypes again, which are sections, which are again sections which are smooth, which are soft. Again, at right, softness, smoothness. At which smoothness and softness, then you get archetypes, and with archetypes you get deepness, because the archetypes are deeply projected over the types. So you go beyond what our usual eyes can see. In that sense, Grothendieck was very Tarkovskian also in spirit. He was looking at something which is beyond our usual eyes. Again here, with the space, the same. The points tend to disappear. What tend to appear are sections. These extensions show that in this world of archetypes, something more smooth or more soft is happening. And this smoothness and happening is the one who explains these kind of constructions in which we can talk about topos non bits sans point. Les points ne sont plus finalement ce qui est important. Ce qui est important, c'est quelque chose de beaucoup plus profond dans les archétypes. The archetypes are projected again on the types, either the sites or the shifts over the site. The archetype is something which appears in the topos, in the general topos, projected over the site or projected over the shifts. So we can see that shifts are everywhere in the work of Grothendieck between 1955 and 1970. Between 1955 and 1970, they are everywhere. They were more or less implicit in his PhD thesis. They are very many constructions of Grothendieck in his thesis are very close to these constructions, and they will appear also, but in disguised form, also in the third period, which is fascinating. The third period around Montpellier. But in this period between 1955 and 1970, shifts are everywhere. Shifts over abelian groups gives you abelian categories. Shifts over rings gives you the schemes. Shifts over Grothendieck topologies gives you the shifts, the toposes. And shifts over something, we don't know what, that's an open problem. Shifts over something should give the motifs, which is one of the other very important constructions of Grothendieck. So there is, again, a wide multiplicity. You take an object, the category, for example, of abelian groups, then you multiply that, and then you take the category of all the shifts of abelian groups, then you axiomatize that, then you have the abelian categories, and then appear very naturally axiomatically shifts. And the axiomatical shifts appear in shifts, axiomatical shifts appear in toposes, and they should appear in motifs in some moment of the development of those, if they become to be understood in some moments. This is one of the great open problems, the standard conjectures, simple conjectures by Grothendieck, extremely hard to prove. Again, some methodological strategies. I have mentioned that. I will go a little quicker. One of the basic ideas is go beyond the thinking itself and pass to the processes in otherness. Then you inject all the time the particulars in the universals, the small ones in big ones. What is artificial becomes natural. What is singular becomes smooth. General idea of Grothendieck. Go from types to archetypes, and then when you have the archetypes, go back to the concrete. Back and forth between the concrete and the abstract all the time. Cover the concrete by a rising sea. This gives you an abstract setting. Problems are resolved. You come back to the concrete. Very simple, extremely profound idea. Very deep and very simple at the same time. And this can also be translated into these words. Towards non-separation. Grothendieck was a mathematician, a person, and a universal thinker in which all the things were connected together, both in mathematics and in life. And could that be ecology? Could that be our very life of the very day? Could that be mystic, theologic? All is connected in Grothendieck. Universal mind. A universal mind cannot accept that things are separated. He looks at the connections between all the possible things. This can be said in this way. The transits, which correspond to complexity, are not entirely determined by separated neighborhoods. We need something more, shifts. Number, which is usually arithmetic, is not entirely determined by separated integers, but by schemes. Space, related to geometry, is not entirely determined by points, toposes. Form is not entirely determined by groups, motives, etc. But there is something always beyond our usual separations. The separations are easier for us to work because if things are separated, then they are more in a sense more grasped by our very hands. Instead, if we allow the connections, then we have to have an open mind, very open mind, which is not the usual of the mathematician. Grothendieck was a very strange and powerful mathematician and powerful human being. The polarities also were, for him, in a certain moment, something very important to him, the yin and yang polarity. Something soft, yin, versus something more architectonic, the yang. The softness and the architectonics were for him fundamental. He invented using yin ideas, and then he constructed gigantic architectonics to show that those yin ideas were correct. The back and forth between them were fundamental. At some moment in his later years, between 1975 and 1991, the years around Montpellier, which were really fantastic also, they are usually set aside, but it's a big mistake. What he did in Montpellier is something very, very, very powerful, at the same level of power of a construction of toposes, schemes, or motives, is something very, very deep, with a lot of work going on. He accepted something very interesting for the philosopher of mathematics, that is that he accepted to write the diaries in which he recorded the ideas as he were invented them. Not as in the first part of his life, in which he invented and then Dieudonné and his school eliminated all the obstructions, and then all was extremely clear. In here, he introduces the idea of a diary, in which he introduces ideas which sometimes are wrong, and he has to elaborate on them, and he elaborates on them pass by pass, in order to show how the construction, the mathematic construction, appears and is invented. So this is what we could call the plastic work diaries, the yin part, contrasted with the architectonic usual construction of the EGA or the SGA. Place to mistakes, place to amendments, place to the progressive variations. The characteristically open-minded of Grothendieck is here present. That's a treasure. It's a gigantic treasure for the philosopher of mathematics, and also for the mathematicians themselves. He works here in a different way. He begins by direct access to rich arithmetic geometric objects, coming back to his beginnings. In his beginnings, he was working with very, very concrete work in topology, in functional analysis, in geometry, in algebra. Then afterwards, he introduces all that in the gigantic categorical framework. But then in the third decade, he comes back to the very concrete examples. And from those very concrete examples, he produces very, very beautiful constructions, the Teichmüller Tower and the Grothendieck-Teichmüller group, the constructions of complex variables, the descent d'enfant, with very simple combinatorial constructions, he characterizes Riemann surfaces by topological surfaces plus descent d'enfant, etc. A lot of work still going on, and still an example of this incessant back and forth of Grothendieck between the unity and the multiplicity. Here he comes out to the multiplicity of all the concrete variations. This multiplicity of all the concrete variations then afterwards propels him to the side of unity again, a great desire of unity, which is the the last work of his known life, or known uh, published or distributed work, and the work of the derivatives in 1991, in which he tries to understand from a unitary perspective the multiplicity of homology and homotopy. So again, this continues to be a back and forth between what could be very deep ideas like this, understand the category of categories with a geometry I, something very deep, which should produce simple enough constructions like the derivatives, which can be projected into different particulars. The particularity of homology or the particularity of homotopy, etc. Again, so a third motto could be deepness implies simplicity, implies softness. If we want to go to something which is really soft, perhaps the good idea is go to the deep. But then the constructions should be simple enough to be projected on very, very wide regions of mathematics. I am beginning, I will have 10 minutes more, beginning to end. So the Yoneda lemma is one example of how the particulars are injected into the universals. Perhaps you know all the Yoneda lemma. It's a name that should be called, in fact, the Grothendieck Yoneda lemma, because Grothendieck proved it exactly at the same time of Yoneda. The Yoneda lemma appears explicitly in the Tohoku. In the Tohoku article appears, of course, not with the name, not Yoneda lemma, not Grothendieck lemma, just a lemma. And the lemma says that essentially any discrete category can be embedded in a continuous category with all the prefixes in the ideal objects complete the given category. At the right, you have the smooth category. At the left, you have the discrete category. Here is what I was talking a moment ago. The elementary toposes produce very beautiful constructions from logic, but using just first-order logic and propositional logic. If we want to go in a more Grothendieck'ian spirit, we should go to higher order logic, and not just propositional logic, but model theory. Higher order logic and model theory applied to Grothendieck toposes is what Olivia Caramelo has been doing in the last 15 years. It's a big shift. This is something that I have also mentioned. You go from the diversity of structures to less forms to less universal archetypes behind forms. So back and forth between, at right, the differentials, at left, the integrals. This is the permanent back and forth between one and the many, continuous discrete. This Grothendieck does it with very, very good success. I think is the most successful mathematician that I know in this going back and forth between all these different aspects of mathematics. And that's why probably he is the greatest mathematician of the last 50 years. Something very interesting is that this great philosophy is also applied to life, to philosophy, to ecology, to art. No, Grothendieck doesn't do it for art, but some of us have done it to understand culture and critical theory using Grothendieck lenses. This injection and projection are two words which are fundamental in Grothendieck from the very beginning. The PhD thesis constantly works about injections and projections between topological vector spaces, With that, he characterizes a lot of properties of Banach and Hilbert spaces, always back and forth, injecting and projecting. Always connecting Riemann and Grothendieck. Here we can begin to summarize. In Spanish, we have this wonderful duality that usually it doesn't happen in other languages. In Spanish, we say corazón for heart, but corazón is exactly the dual of reason. So the usual duality which comes from Kant between intelligibility at right and sensibility at left, between reason at right and heart at left, becomes in Spanish a truly dual construction between razón and co-razón, which is corazón, which is the heart. This back and forth between yin and yang, sensibility and intelligibility, between archetypes and types, very, very Grothendiekian. Dilemmas that I have mentioned, I have summoned here. Unity revealed through multiplicity. Abstractions dissolve obstructions. So abstractions are never artificial. They are the way to understand. Deepness enhances softness. I should put in the middle simplicity all the time. Simplicity all the time, navigating. So I finish here. Olivia, thank you for the invitation.
Thank you so much for this marvelous talk.